All yours.
All right. Thank you for that warm welcome. So my name is Paulo. I'm currently working at Precor. Precor is, they make fitness machines. So put a picture here. You guys know what Precor is? Yay. So there you go. That's the building where I work. It's half the building. The other half is hidden. And in case you want the inside scoop of Precor, here's another picture. So, as you can see, it's very messy. This is my little side of the world there.
Where the treadmill desks.
Yeah. No, we don't have treadmill desks, unfortunately. But we do have the consoles, those which, just the head that goes into the machines. You can test them and play around and whatnot. Mine is turned off. This is the end of the day, I guess. So,
do they use machine learning?
yeah, so that's what I'm going to talk about. So we're going to talk about machine learning. It's going to be very introductory. I am no expert, I should warn you guys. I've been using it for a little bit, so I'm going to share the experiences, what I have learned so far, and just introduce you to machine learning and data mining. Hopefully, get you excited about the topic, and you do your own research and get inspired and whatnot. So up front, if you don't understand my accent, just shout and I try to repeat. So anyways, this is another inside scoop of our Scrum board, I guess. It's pretty long, and there's no activity because it was the end of the sprint, so you don't see any cards in there. Anyways, this is why I share the internal. With that, let's jump right in. I don't have an agenda. Just like a movie, it will develop by itself. I'm not going to tell how it's going to end because then you're not going to stay here. It's not fun. Anyways, I guess what those two companies have in common. Can anyone guess? Target and Pandora?
Machine learning.
No.
Both of them lost user data.
I'm going to give you more data. How about that? How about all these companies? What are they doing? If I feed you with more data. Yeah, you're right. They're all doing some kind of data mining, right? So be it for selling you advertisement, making sure you buy some products, or selling their products. Either way, they're using data mining and doing machine learning, of course. There's also this other, well, it's not a company. I guess it's a talk for another time. Anyways, we're doing lots of data mining and machine learning, as you can guess. Maybe for some not so good purposes. But on the target subject, the reason I put target in there, it's I don't know if you've seen this in the news. It's old news. It was about 2 years ago. They sent a letter to a family talking about, hey, the father didn't know his daughter was pregnant, and she was a teenager, right? And it was pregnant, and Target just said to her, welcome, you have a baby, awesome. And it didn't went too well. So if you're doing a data mining, just make sure you think about ethics before, right? So, I guess it's exciting to use new technology, but don't do that kind of stuff. More recently, Pandora just announced that now they know your political affiliation based on your taste in music, I guess. So they kind of know where you're listening, your geolocation, and whatever music you're listening to, they think they know.
So you're listening to Ted Nugent? So
I don't know. But anyway, so they're trying to target advertisements for politicians in election day based on that kind of demographics. Go figure. So there's many creative ways of using this way, and I just hope people will use it for better than for weird stuff. So with that little introduction thing, let's jump right in into data mining. So what does it take to do data mining? There is this new field called data science, right? And it's basically it's a synergy between a lot of the sciences. You have to know hacking skills, programming skills. You need to know math and statistics, and then you have to have domain knowledge. So if you have all these three, which is pretty much impossible in a single person, then you're literally doing data science. Otherwise, if you like me, have some hacking skills, and some domain knowledge, you are doing dangerous stuff. Because without the math to back you off and the statistics, you may be totally off. So that's why you're in the dangerous zone if you don't have a math guru on your side helping you out. People from traditional research, they are basically, they have a lot of domain knowledge and no math and statistics, but they're not using computer for data mining. So that's basically the field of traditional research. Everyone from traditional research seems to be shifting here, right, into this data science. That's the sweet spot where everyone wants to be. However, that's the data scientist profile. What does it take to be a data scientist? You have to know computer science, math, statistics, machine learning, domain expertise. It sounds like a typical job advertising, right? They want you to know the whole thing. Yeah, communication, presentation skills, somehow it's always there. Anyways, it's pretty much really hard to have a real data science. So what companies like the ones I presented before typically do, at least Google, is they get people with different skills and they form a team. So one guy know a lot about what is this? The blue may be statistics, so green is one of those three things: domain knowledge, and they put them build a team with that knowledge, and hopefully they will do data science. So why do you do this whole notion of data mining? Is that you want to go from data to information in order to make predictions, right? So it's this whole idea with information you gain some knowledge, and knowledge you gain understanding, and you become this guru here. But if you're this guy, you make a lot of money. So anyways, so that's the pyramid to wisdom. You start off with noise. You have log files, and you have databases, and you have data spread throughout your organization. You capture those into some kind of a database. From that, you derive information, hopefully from information to knowledge. And once you do that several times, you totally gain understanding, and then you become this wise guy. Yeah. And just like the New World Order, the top of the pyramid, you know everything. Anyway, so I've been reading this book a lot. That's where I started. It's data mining with practical machine learning tools and techniques. It's a pretty decent book. It's kind of easy digest. The math is easy. They introduce you, and anyway, it was mainly some kind of recommendation engine suggested this book to me. So it's kind of a meta, recursive, whatever. Anyways, and then the other one is Mahout in action. I wanted to do something with Mahout here, but I don't think we're going to have time. I'm just going to focus on the data mining aspects. So let's jump right into it then. Typically, you have a table like this, right? You have, this is, I guess, a weather-related data. You have outlook, sunny, overcast, and rainy. Temperature, hot, mild, and cool. Humidity could be hot, high, normal. I guess high and normal. And then windy. So with these four attributes here, someone is trying to decide if they're going to play some game or not, based on the outcome. So, when it's sunny, hot, and high and false, you're not going to play the game. I guess it must be an indoor game or something. Anyways, so what we're trying to do is to give them a new set of data which matches these conditions, right? Sunny, hot, high, and false, kind of predicted the outcome. And that's called the classification problem. When you want to predict a value, it's classification problem. So in this case, the value played, it's nominal, right? That's also called supervised learning. If the value were to be a numeric value, like let's say stock price or something, it's called a regression problem. I'm going to focus mostly on classification here for this talk. So feel free to interrupt anytime and ask questions here, but this is just laying some groundwork and also some examples. So basically, then what's machine learning? Software systems that can learn from data, right? to make useful predictions. And the classical example you see in books is spam filters. You don't program a spam filter every time there's a new text, right? It learns from the data, it learns itself. So without having to reprogram it, it's learning from data. So that's pretty much the machine learning. It's kind of a misnomer, right? Machines they don't learn, but that's, maybe they do, I guess. Anyways, so the class is the attribute you're trying to predict the outcome for. And when we're running a machine learning algorithm to predict a class, we call this a classifier. Classifier is the thing that predicts the class. So here, there are several machine learning tools out there, and the one I'm going to pretty much focus about is this Weka stuff. It's not Weka, it's Weka. It's Waikato Environment for Knowledge Analysis. It's pretty famous as a Java library, and it also has a workspace, this GUI component, so you can interact with it in many ways. Typically, people will use the GUI to come up with, choose an algorithm and do a bunch of evaluation and tests, and then you hit the button and generate code, and then you write that code in your application. So, anyways, it contains a whole bunch of algorithms to choose from. Let me just show you a little bit about it. So, just going to start over here. This is live approval. So there you go. You have this little weed here. Doesn't mean much. It doesn't seem like much, but each one of these things comes with a different tool. You got this Explorer, Experimenter, Knowledge Flow, and simple command line interface. And there's a whole bunch of visualization tools here. So if I open up the Explorer, several tabs here. So I'm going to choose. Let's see.
So just out of curiosity, does a classifier, is it able to modify like a class on the fly or something?
No. No, it's not able to. So there are tools to modify the attributes on the fly. There's a whole bunch of what we call feature engineering, which is kind of adjusting the attributes to a value that's going to give you a better prediction. So that you can do. But changing, typically you want to, make the machine learning algorithm predict the classifier, the class, right? I will show you more as we go through. I guess we'll become more clear. But anyways, so I opened that file that we talked about on this slide, basically. So in Weka, you can set up a data source to a database, and then read tables and write your own queries and build stuff from, create a view, and that will bring that data into memory, into a table form. But Weka will save into what is called ARF files. It's basically the format that Weka needs the data to be on. So if I open up this WAR file, just to give you an idea what this says here. I have several examples that come with the tool. The weather, nominal thing. Whoops. Anyways, if I double click, it shouldn't have done that. Let's just do that. So you can see the extension, it's ARF. Is it too small in there for you guys in the back? But that's what it's basically a CSV file with some meta tags. You got the data tag in there and then attributes describing the type of the data. So it's a very simple format. Anyways, so if you open a file like this, what you get here on this left panel is all the attributes will show up, right? And as you hover over the attributes, you see that it constructed this graph here in the bottom, which is in itself, it's like a histogram. So it tells you how many instances that weather data has. So only 14 rows. And for each attribute, it will tell you how many different classes of the attribute it has. So kind of sunny, overcast, and rainy. And then we'll do a count for each one. And the graph reflects that count. So, so class is the thing we're trying to predict the outcome for. Usually it's the last attribute. So display attribute here, it's the last attribute. That's where we're going to predict the value for. So let's jump back to the presentation here. We'll go back to Weka in a second. This is what I was supposed to do. Anyways, I'm not getting to that detail. So here's the process. You start with a training data set. The training data set is the data set that you know the class. It's already there. And you feed that into a machine learning algorithm. That will produce a classifier. You feed some test data. And based on the test data, it will tell you, you're going to evaluate the results, iterate over, and if you're happy, you deploy it. So the test data is something that you know the class. It comes from a same population of the data, but it's a different test data. In theory, you're supposed to have this infinite population of test data, and you choose one piece for to feed your classifier, that machine learning algorithm, and another piece to evaluate the data, if your classifier is predicting correctly. So you're going to get the percentage of the estimation of correctness, and based on that, you know how good it is.
Are you using JUnit or anything for doing the testing on this, or what are you
No, there's nothing about, there's no JUnit here. This is, it's in machine learning, the typical approach is, they call it test data, but they're not running JUnit. You're feeding the classifier with test data. So the classifier gets two inputs basically. The training data set and the test data set. With that, then it will produce your algorithm. So it's going to use the test data set to evaluate how well the machine learning algorithm it's predicting the outcome. So,
Hey, Paulo?
yes?
So if all you start with is a big lump of data, how do you partition that?
Yeah, so that's a great question. So we're going to talk about that in subsequent slides.
Okay.
Because the huge part of this, you're right, is figuring out the data, right? Which, how do you go by designing the data that you're going to feed the algorithm in there? So we're going to talk about
Okay.
it.
Okay.
So let's say you don't have test data. One common practice is to take the training data set and take 66%, for example, for training, and the other 33 or 30% for test. So that also works. The idea is that you can, just randomize here and choose a percentage for test. But there's a basic assumption in this. You don't want to mislead your classifier. You don't want to gain it. So you basically literally have to, just use a small portion of the training for test. And that what's small and what's big is really going to be a problem. How many attributes there are. It's a subjective interpretation here. So I don't know about you guys, but super hot. Excuse me. So, anyways, so this is a better illustration, hopefully. So you start with attributes in classes that you already know the outcome, right? A test data. You break it in training data and test data. use a small portion of it for test data, typically 33% here and 66 over there. So then you feed the classifier. The classifier will run a machine learning algorithm of your choosing. We're going to talk about 4 different kinds of algorithms in this presentation. But the classifier will ignore the class. It's going to use the test data ignoring the class. So it's kind of like, imagine if you delete yes and no, you're going to play the game. You just have, the weather attributes without the yes or no. And after that, it's going to use the predictions, test the predictions based on the data from your test data. So literally the test data is used to evaluate how well your machine learning is doing. And that's what they call the holdout method. Holdout method is just basically splitting your training data in a test setup with some percentage. That works quite well, but there's a better method that's called cross-validation. So with cross-validation, you take a data set and you cut in 10 pieces. And you choose one slice here for test. And you train your classifier using the other 9 pieces. And then you repeat the process. You choose another piece for test. And you go on and on and on until you iterate all the 10 parts. So this gives a much better prediction. It's the same data set, but it's how you randomize it and the fact that you're dividing into. So I'm going to show you this through the Weka tool in a few minutes. It's going to become a lot more clear as we do it.
But how do you save the model in between each? I mean,
Okay, let me, how do you save the model?
well, I mean, if you're running it through 1/10 of the data each time, or you're running it through 9/10 of the data each time.
Yeah, so the tool does all that for you automatically. So this is just explaining what the tool will do. So you feed it one test data and you say, I want cross-validation. The tool will pick up the entire data set, divide in 10 segments randomly, and use 9 segments to feed the machine learning algorithm, to feed the classifier. And then you use that 1/10 of the segment to test the prediction. And then we rotate over and over and over 10 times. Weka will do this 11 times. And then from there, hold on a second, it will produce, generated code for you that you can use if you're happy with the predictions, how well your classifier did. That
So
gives you
can
an
you pick
indication.
which one you like the best and use
Oh
that
no,
one as your model?
it's one process. You're not choosing one over the others.
No.
You're using the collection of these things to better tune the machine learning algorithm.
Does it reset the model then each time after, after it goes through 10/10 and then has to wipe out the last learning prediction and try again with the...
No,
with
it
the new-
uses an average of those. It doesn't set the model every time. It will combine those. It's gonna average out.
Well, actually, the answer to that question was yes. You only retain the result. He was asking, do you keep the model between them? You don't. You could construct 10 completely independent models, but each time you train,
Right.
you forget the previous model.
Okay. But yeah. Okay.
And then the 11th model, you train on the entire data set.
So is there
Sorry.
some arcane statistical wizardry behind the number 10, or is it?
Yeah, there is a whole bunch of statistical wizardry behind the 10, and that's stuff that I don't understand exactly how it works. Here is the statistical wizardry. So for example, the holdout method. Let's say you do it you take 10% for a test data set, and you use the other 90% as a training data, right? So you run that one time, and you get 75.3 correct prediction, percentage-wise, right? So you do that again, randomize again, and then choose another 10% of the data set. And then because it's a different data, you give them, 77.9%. And you do this 10 times, and you average out, right? So that's the math they do, the simple mean and the variance. The goal is to have a standard deviation very small. So the cross-validation thing that does that automatically in the 10-fold thing give you better sigma here, much smaller than the other one. It's all statistical, but it does give you a better
So
one.
it's just if you want to publish your paper, you need to say you did 10-fold cross-validation, like you have p equals 0.05.
Yeah,
So I
exactly.
think the answer to the question is, 10 is not a magic number, it's a trade-off.
It's a trade-off, it's k-fold, right? The real thing is k-fold. So 10 is typically what people do. It could be more or less, but if you do too much, you don't get any benefit. So in practice, it's shown that 10 is the number that works best. But I guess it depends on your data set too. So
If you drove K up high enough, though, are you overtraining? Are you starting to cheat? Because
Yeah.
you would actually end up, essentially you're not really testing, right? Because you're actually training off the whole data set.
yeah,
And so there is a trade-off, right?
There is a
It's-
trade-off.
It's a smaller sigma, but it's less, it might be less powerful as an actual predictor. But you
Mhm.
kind of train when you test.
yeah.
Okay.
So what you're actually measuring is that if there's a significant difference in either the model that you get, either the knobs that it sets, or the results of the classification, then you're using the wrong model and methodology.
Yeah, it's gonna help you.
And the signal will be
Yeah.
huge.
So it's going to help you decide which machine learning algorithm you should be using. You know, which one is going to give you better prediction. So you're going to see more on this as soon as you start running them here. It's going to become more clear. So, all right. So let's talk about the machine learning algorithms then. First one we're going to talk about is this 1R. None of these things are maybe with this. Well, let's just talk about the 1R. So 1R is, you know, it's 1R is one attribute that's going to be used to do all the work. It was invented by this Canadian guy here. It's a very simple method. It uses a single attribute in the attribute data set to make predictions. The trick is which single attribute will do better predictions, is to choose that single one. And this guy did a bunch of experiments with 16 data sets using cross-validation. And he said, his paper said, hey, you know, simple rules often outperform far more complex algorithms out there, just using one guy to predict. And why does it work so well? What he said is because some data sets are really simple, and you know, a lot of them have noisy, complex, that can be learned from them. In real life, the data is very noisy, so you can't learn much about noisy data. Then 1R will work. To choose that attribute that's best in a predictive classification, it uses this algorithm here. It's basically for each attribute, for each value of the attribute, make a rule as follows. Count how often each class appears, find the most frequent class, make the rule that assign a class to this attribute value, calculate the error rate for the attribute, and then choose the one that has the smaller error rate. It's kind of complicated, but it's pretty simple to understand if you see an example. So, for example here, say that, you know, the outlook, the weather data, right? Taking the attribute outlook, you just list all different values that it shows up: sunny, overcast, and rain. And you basically count, it's going sunny, one no, another no, and you go here, sunny, another no. So there are 5 sunnies total, but it's leading towards no, right? Because there's 3 out of 5. So then 2, it's going to be yes. 2 is considered error because it's leading towards no. So then you pick, say, 2 out of 5, that's the error for that sunny given no. Did everybody got that? For overcast, for example, you look at here, it's predicting, it's leading towards yes, yes, overcast again, yes, yes. So there are no errors, it always gives you yes. Then it's 0 on the 4 times that it shows up. So you do this over and over for all the attributes, and then you sum up. You know, you add up 2 plus 0 plus 2, 4 on the 14, and over here was 5 on the 14. Oh, there's a tie here. So then the machine is free to choose. When there's a tie, it's going to choose either outlook or humidity. So one of these guys are going to do the best prediction. About the same for outlook and humidity. So you just choose one row. Yes?
So, Paulo, what does the play column signify in that left table?
The play is the attribute you're trying to predict the class for. It just means play some kind of game. So you're going to, let's say you're trying to, you're basically trying to predict if you're going to play a game or not based on several attributes.
So when it says yes, it means that it was successful, or?
It says that with this combination of data, overcast, high, and false, people did play the game.
I think this means like, did you have a soccer game that
Yeah.
Yeah.
you took place, right, or something?
Oh, play it.
You know.
Yeah, it's
Or
play the
you
game.
could think about, did they pay you money? So, and yes, is they're paying you money, and so you were trying to figure out what combination of those things are gonna drive them to pay you money.
Yeah. So I should have given an intro, what kind of problems we're trying to predict here. But yeah, so this is classification problem. It's basically a set of attributes. It's basically, what's the probability of getting player node depending on these things, right? So.
Do we draw any interesting inferences from the fact that we have 2 winners by a small margin and 5 14ths versus 4 14ths? Is there any interesting thing we can say about that?
Yeah, you can say that this is better because 4 under 14, it's a smaller error rate than 5 under 14. So
But not much.
It doesn't matter. It's smaller. The machine, it's a computing algorithm. It's going to choose the one that's smaller. So it may not be like much, but for this data set, it was significant. That 1 bit. So.
If you have access to a domain expert, do you even need to run this algorithm? You can just ask him like, what's the best predictor of whether the game is going to take place or not.
You ask, yeah. So this is, let's say you don't have the expert at hand, right? Remember the expert systems that people talked about in the 90s, whatever. So this is a way to replace the expert. Basically, you take the knowledge of the expert and you fit this table with that knowledge, and then.
Well, the expert could have come up with the rules, so then afterwards you can run it on data. You don't need to have the expert present, but like if you build the rule without the expert, that's asking for trouble, right?
Yeah, if this data was totally randomized, it has to be real, it has to be meaningful.
Like you may have heard there's this old story that goes around about the machine learning thing where the army used it to classify tanks in some way, and in the end it turned out that like one set of pictures they had by coincidence like all the enemy tanks that had shot the pictures on a sunny day and all the other tanks on the rainy day. So they ended up basically, the classifier kind of worked, but it was just, it wasn't telling is it the enemy or a friendly tank, it was just telling is it like a sunny day or not.
Yeah, that's why you need the domain expert, right? You can't just start hacking stuff. So you need to, the data has to have some significance. You better be able to, inspect the data and figure out if the data.
I guess that's a problem. I think in this case also there is a neural network, but I guess maybe we'll get to that. So there you can't really inspect much.
So let me just run 1R so you guys see what it means here. So you go to classify and you pick an algorithm, and there's a whole bunch. And Weka has a tool, I didn't show it before, that you can download more of these things. There is a repository out there, and people are contributing and improving the algorithms and whatnot. So 1R is over here. So it selected cross-validation, and you just hit start. And it's pretty fast because it's a very silly data set, it has only 14 instances, right? So, and what you want to see is, look, the classifier chose Outlook to do the predictions, just like we had described. So now you kind of understand why it chose that. And it's saying that it correctly classified 6, it did, using the test data that it's sampling the cross-code. 42% and 57%. So it did pretty poorly. I guess, yes or no, if you're guessing, it's 50-50% chance, right? Are you going to play or not play? Just guess, it probably would be better than 1R in this case. Because, what are the chances, right? It's just 50-50. But, anyways, down here you got this interesting stuff, the confusion matrix. This is yet another thing in machine learning. It's a matrix, it's a 2x2, it's pretty small here, but the main diagonal, it's everything that it correctly did, and everything off the diagonal are errors. For example, it did 5, there are yeses, it was classified as no. Where's the other edge? Yeah. So, I'll show you better when I have a confusion matrix, it's easier to see. Anyways, that's 1R. Huh?
What's a kappa statistic?
Oh, there's a whole bunch of stuff here that I have no clue. So it's a bunch of detailed statistical things, you know, kappa, and I don't know.
Is it just like one number that would be the best measure of like how reliable this, how much confidence would you
Yeah,
have in
it's
this
pretty much,
classifier?
yeah, what I'm going for is this percentage here that I'm looking at. Because like I said, I don't, remember that triangle, I mean, the first slide, the math and the statistics, that's the piece I lack now, right? So my own interpretation of this is, hey, look at the correction, the percentage here. And I'm pretty sure this means something, but it means more for a statistician.
You know, like if it got 60% correct and if it's the data set like 10 items, that's not very impressive. If it was like a million, maybe that's more impressive, I don't know.
Yeah, I'll answer that question once I learn it myself, so I don't know. So in this tab here, I just want to show you this. Output source code. So in production, let's say you're happy with this classifier. Like, oh, this is awesome, it's a good prediction. In this case, it's not, because I just get very little data. It's only 14 instances. You're not going to do this in real life. Plus, this is a bogus, it's a totally bogus made up thing. That's why it's kind of giving you know, this poor prediction. But you just run start button now with that option. Oops, I'm running twice. And you get the little code here. So that's the classifier that it built using the Weka. So you can literally copy and paste this and then feed real data and we'll give you the prediction. So that's, I guess, typically what people will do. Once you have live data, you want to feed to the classifier, generate the code, and then you can reuse it to make predictions.
So,
Anyways.
has it been rewritten for Java 8 so we can make
No,
this
sorry. This is old stuff. Hasn't been written in Java 8.
Looks like it'd be a good candidate for parallelization.
Yeah. So
Yeah, more important, does it run in the cloud?
Yeah, that's good. A bunch
Or more
of-
serious, is it compatible with like using it with Hadoop or Mahout or something?
So a few algorithms are, but this wasn't built with Hadoop in mind. You can set up a cluster of Weka machines, and they will talk to each other in the command line mode. I haven't tried that. They say they support big data now with this approach. I haven't tried. But there are better things for more big data out there. And I have a slide with a few names, a few options you can try. Anyways.
Just really, that, can you explain why it did so badly? I can't quite figure out how it got from the 6
because
right.
they did
10, but we said that the classifier was 10 out of 14, right? So
Yeah, it's.
So even if you drop 1, you should be no worse than 9 out of 14? Like if you drop 1 that it was correct on? So how did you get only, you only seem to be only getting 6 out of 14, right?
Yeah, let me go back to let's see.
I mean,
There's the data, try to do better.
well, we could do better, but I mean, but it's just what was shown on the, it didn't, I don't understand the output from the 1 hour output.
Oops. Let me get rid of the source code here.
Sure.
Or I can just click here and see.
Yeah, right here, right? Like it says above 10 out of 14 instances correct, it's the classifier we're trying?
Yeah,
Above
it's
10 out of
about the task set that it used.
Yeah, but,
Right.
but if it's doing 10-fold, isn't it doing, dropping 1 and testing on the rest?
Yeah,
So
but
it'd
it's
be
still
9
a
out of
very small
14.
set. It's still a very small, there's
So
only
should it
14
only, if it
instances.
drops 1 that it would be correct on, it would
Yeah.
be 9 out of 14, which is still more than 6 out of 14.
Yeah, but it still predicts it poorly. Go figure.
All right, well, something I think we're missing about what it's actually testing, right? I mean, I don't, I'm
Oh,
just defining
what it's
testing.
testing.
So it's saying it's only getting 6 right out of 14, but that answer gets 10 right out of 14.
Whoa,
So you can try to visualize what's it doing here. Let me see if I can come up with a. Oh, you know, I'm going to show you on this other data that I have. You see what it's doing graphically speaking here, and will become more clear. So just bear with me.
The results of the 1 hour test are no different than we calculated by hand.
Yeah.
They're the same. What's different by taking the 10 passes is these statistics that you've generated, the big chunk in the middle.
So let's try to use, for example, percentage split. That's the holdout method, right? If I run this again, you get 40%. So it shows you that cross-validation here, the first one,
right.
42, so it's slightly better, just like you saw in the slide. At least it's matching it, the theory, right? The holdout method is slightly inferior than the, but in this case.
Oh, because the test set is not the 9, oh, that's right, because the test is only the one instance.
Yeah.
Okay, okay,
So-
now I get it, okay, I understand, okay.
Let's move on to another famous one, naive-based method then. So this one here is use an opposite strategy. Instead of choosing a single attribute, it's going to use all of them. There is a few assumptions about it. It's every single attribute is equally important, and they're statistically independent. Meaning, it's going to rain tomorrow. It has nothing to do with I drink coffee today or something like that. If the prediction, if the attributes combined had some meaning together to generate the outcome, this wouldn't work well. So they better be statistically independent. Then you would choose naive-based.
Now, it seems to me that with your example, humidity and whether it's raining or not, it's probably not statistically independent.
Yeah, it's probably in this example or not. It might be, and that's
It depends on your definition of rain.
Yeah.
Yeah, I suppose. But can it still be a useful method even if you're kind of fudging on the statistical?
Yeah, it is. It's what it's saying here that independence assumption is never really correct, but it really doesn't matter. Often works well in practice. So, anyways, this is a better. Let me do a bigger plane here. Forget it. Make like this. So this is the whole method described here. It's just it's using probabilities, right? It's probability of the hypothesis given some event. A priori versus a posteriori and whatnot. So, anyways, not going to get into much details in the formula, but let's just run through one example here to see how it works. So here's our table, right? When you want to do this is your original data here. You want to just simply count how sunny led to yes 2 ice and led to no 3 times. Overcast led to yes 4 times and to no 0 times. So you just do a count and you sum these counts. So there are 9 yeses total and 5 no's. So for sunny, the total is 2 out of 9 for yes and 3 under 5 for no's. So you do this counting for each one of the things, right? And then, well, you're not going to do it, but the machine's going to do it for you. So let's say there's a new day, and you try to predict yes or no here. So it's going to apply the formula, sunny, you look at sunny, and for sunny it's 2, 9, so it's going to be 2, 9 times cool, where is cool? Cool, the total was 3, 9 times 3, 9. Then height, you look at the table you build, what is height? It's humidity, height, the total is 3 out of 9, so, and so on and so forth, and produces this number here, right? That's the probability for yes, and that's the probability for no, and then it normalizes this. It's basically, this is normalizing probability, and you get this number here. So, it's likely to be no because it has a higher probability, right? That's basically the naive box. So, that's just explaining the whole thing here. All right, so let me show you real quick. Running this.
Are you going to make these slides available to us on the website?
Yeah.
Right.
Oops. So later I'm going to talk what I did at Precor using this stuff and show you a large data set and show how the algorithms run and why did I choose one versus the other, that kind of stuff. So there's a little bit of insight on the practical aspects of this at the end of this talk here. So let me open the real quick. I didn't mean to close the other one. Now I'm going to open the file all over again. So let's open the Redmond. You go here to classify table, and you choose naive-based. You could double click here and set up options. Every single algorithm has different options to set it up, so you can tune it. And then let's just run cross-validation. It's pretty fast because it's a bad data set, small data set. and you can see what it did here. So the difference is that, remember the probabilities you saw? It's building that probability table. The difference here is in Weka we will adjust every time there's a zero something, so you can't multiply by zero, right? In the case of the, what's the sunny? Which one was zero? It's one of these guys. Yeah, overcast, for example. So it's basically, it shifts everything, adds 1, so it doesn't multiply by 0. Otherwise it would screw the probability formula. So it adds 1, it starts with 1 every time. Anyways, and then you can see the probabilities here, and this did a little better, so 57%. So it's a better machine learning algorithm for this kind of testing. Yes?
Okay, so Baba, what's your confidence level that you will remain within, you know about the z-test and the t-test? Have they mapped this according to the, the accuracy within certain confidence levels?
Yeah.
Because it looked like the extending the test domain out of the it was sort of a version of the central limit theory,
Mm-hmm.
And then, so it should correlate to a certain confidence level, right? At a certain amount of, that you can.
Maybe that's the mystery kappa value.
Well,
Yeah,
kappa is about agreement. It's
mean
not
absolute
about
error, right? I mean, that's-
confidence number.
That error, there's an error term which is exactly that, right? That's telling you how much confidence you have in the output. I mean, it's one of these things,
I can't
it's
see
root
nothing
mean
back
squared
here,
error. Well, it's in there. There's a root mean squared error, which would be standard, right?
It's in here, you got a standard deviation, it's down here. It's one of these guys.
Yeah.
Root mean square right
Yeah.
here. You got the relative mean, there's different
Right.
ways of measuring how it deviates, right? And they're all calculated and computed down here. So, anyways, so we saw 1R and 9 phase. Let's move on real quick here to the next one. The other one is decision tree. Decision tree is actually used a lot. So it uses this top-down recursive divide and conquer approach. It's basically, so it's going to select one of the attributes to be the root node, and the trick is to select which attribute to be the root node. And then it's going to split, like sunny, overcast, and rainy. It's going to choose the next node in the tree. Let me show how it's doing that real quick here. So let's say, outlook sunny, and it's counting the yeses and no when it was sunny. When it was overcast, you got 4 yeses. So each time there's a peer outcome, that's what you got when you want. You want to select the things that give you the most peer answers. Either yeses or no's, but no mixes. So behind this thing, they have this whole thing about the information theory, that it uses this notion of entropy, and it calculates the amount of information gained by knowing the value of the attribute. It's some entropy math. I'm not going to get into details. He probably knows. And then, anyways, once you run to the entropy formulae there, you got this information gain in bits, and you have fractional bits in information theory. So, anyways, this guy has higher bit rate, so it's going to select output just based on the entropy of the yeses and nos. So it will do that, and then choose output as the root node, and you do that again to choose the next node. So the next node in sequence, if you look in here, with the one that has the highest gain using the logarithmical entropy formula was temperature. So it's going to build a tree then using temperature as the next node. So it's just basically your decision tree then, constructing that based using information theory. So let me show you. This is actually cool because you can visualize the tree. So let's choose a different different one this time around. That's a tree-based, and J48 is the name of the tree one that we're gonna pick. And if you do start, you can see that it built a tree here. It's hard to see, it's a text tree, so you can visualize the tree. So it's kind of small, but you can see that it did exactly applied information theory there, and it shows when it's sunny, humidity, when it's high, it's going to go here, and so on and so forth. If you were to generate the code, you'd see a bunch of if-else branching. So it did that from the data. So if I change here, more options you can see the code. See a whole bunch of these else and whatnot. So that's the code you're going to use to fit the new data. Anyways, that's kind of cool, I think. Back to the slides. Hey, how are you doing the timing, Nimrod?
We've got plenty of time, 45 minutes.
Okay. All right, so the final one I'm just going to go over today is the nearest neighbor. And that's also called rote learning, a simple form of learning. It's the lazy because it uses the instances themselves, they represent knowledge. So, and do no work until you have to make predictions. It's easier to see in the graph presentation here. Like, for example, you have a few things that are blue, and a few things that are green, and you have some red in here. You want to classify this guy. It could either be blue or white. So this basically takes the distance here, and this guy is closer to blues, so it's gonna guess this is a blue thing.
So just take any two in the two camps?
Huh?
And take any two pair from the two camps?
Yeah, so it's basically, it's gonna look around, right? Am I close to a blue or am I close to a white guy? Oh, I'm close to a blue, so therefore I must be a blue.
Well, you have to look at them all.
Closest two.
It's not a pair, you have to look at them all.
Yeah, you
Oh,
have to look at
that's
all
the
of these
expensive
guys. I'm just giving you one example,
Oh, I
but
see.
it's gonna look at all of them.
Okay.
Yeah, thank you for that clarification, yes. So, what you want to fit this thing is the notion of similar. So you need a similarity function. It can either be like a Euclidean distance, the one you saw back there, or it can be this Manhattan distance, which you use a city block. And so it's just a different formula to compute the distance between 2 points, right? And but it's going to do that for all the points, just like you said. Anyways, it's called, this is the K factor, I guess, right? How many, you can use, instead of just comparing against 1, you can compare against 3 or 4. So you can increase K to give you better, I guess statistical comparison results. And there is a mathematical proof on this, that if the size of n, which is the number of instances you have, tends to infinity, and the size of k, which is how many neighbors you're comparing against, also tends to infinity, then k under n gives you 0 errors in the prediction. So this one helps if you have a lot of data, and then you have computing power, right? A lot of data and computing power, and you compare everything, then you have a 100% prediction or something. 0 error.
As n approaches infinity and k approaches infinity, the computation time approaches infinity also.
Exactly. Exactly. So it depends on your computing power, I guess, and how much you're willing to wait. The previous example was K1. So this one is more interesting to visualize it, I guess. Let me show you this visualizing. So you go into Weka tool here. I probably shouldn't be using this weather data. Let's pick something better. classifying. Oh, iris2 data. Also, this iris data set is pretty famous in data mining. It's sample used everywhere. And it's basically about iris setosa, is that how it's called? It's a plant, it's a flower. There's 3 kinds of flowers depending on the size of the petal or the length of the petal. So let's use that one. I don't have internet connection, do I? No, okay, doesn't matter. So let's go back here, open file, and let's use the iris2D. The reason I'm choosing the iris2D, 2D means here there's only 2 attributes. It's because it's going to be easy to see in the visualizer too. The Weka visualizer has a limitation. You can't visualize 3D or any dimensions. It only allows you to see 2 dimensions. There are other tools out there that you can see a whole bunch of 3D dimensions, and it's kind of cool stuff. But so if we look at this data here, real quick, it's basically so there's a bunch of instances this time around 150, not a lot, but petal length and petal width. And basically, the class, it's what's trying to predict which type of flower it is. So it can be 3 kinds, either iris setosa, or virginica, or something else, versicolor, right? So actually, I mean to show you the visualization tool, this boundary visualizer. I'm gonna have to do all of them. Where's that thing? Data. iris2D. And so you can see the 3 classes here. So, and if I choose a classifier, and let's choose which one?
Lazy.
Lazy. Thank you. IBK. So, let's start this one. And
That's gonna.
you can see that, before classifying, you saw there was a bunch of reds here, a bunch of greens there, and the field mix between blue and green, right? So it's detecting these points, and that's basically how the algorithm is thinking. And the K here, you can adjust the K. K equals 1, see that? So if I adjust that, I can say, let's say 5, hit OK and start over. You can see that it's making almost like a 3D picture here. There's this fuzziness around. That's what the K is giving you, because it's looking at comparing against more points. And so there are a few points that are in between, right? Some things that are in between green and red. You get this 2-color space thing. So if you were to simply run it over here on this side, and then classify, and choose, whoops, not J48, lazy IBK, and look at that one, it's actually doing pretty good, 96%. This is more realistic data. It's actually data that was observed on the field. It's a very old data set. It's not a made-up thing. So if you have good data, you're probably going to get some pretty good predictions out there. Anyways, so just for comparison's sake, let's choose another one, the 3-1, J48. And if you hit start, oops, I still have output source code which I don't want. It's about the same, right? So you get the confusion matrix here 49 instances out of 250 were correctly classified as iris-cytosine, but there was supposed to be an iris-cytosine that got classified as a versicolor. That's what this one means. So, anyways, that's it for this learning algorithm. Someone raised their hand? No? Got a question? Okay. Let me close this. Back to the slide thing. All right. The other thing which I don't have the samples here, so it's going to be a bit boring. At least I'm going to mention it. Mahout is an Apache project that we only showed so far classification problems, right? Which means supervised learning. Supervised learning because we fed the class. Like there are algorithms that you don't know the outcome and you wanted to classify. That's the clustering stuff, the unsupervised learning. It's basically, it's going to look at your data set, it's going to find things that are common by some kind of classification, right? So that's the clustering piece. Mahout supports recommender engines, has a whole bunch of algorithms in there for building recommendation engines. It uses recommenders for, the Netflix case, for example, or you want to Amazon shopping cart, you bought this, you like this, that kind of stuff. And they also have clustering classification, but this is just an example of, have you guys tried Picasso with the machine learning for recognizing the photos automatically? Have you done that? It's actually pretty cool, I can show you. Let's see. I had a bunch of famous people here. If I had internet connection.
Actually, you can connect to 4th and Madison, I think.
There's also one for the conference room here.
Oh, can I connect?
There's it's a Heinz conference. You should see it. It should be Heinz, that first one, that one. You can probably do the other one as well.
Okay, cool. That was cool. So, you basically, I'm going to go on the internet, find one of these celebrity photos, and see if you can automatically classify based on the ones I already have. So it gets better and better as you have more photos. Yeah,
It's not very good, but it's...
This one seems to be pretty decent. When I put the banderas here, the second photo to classify, then I put this third one here, it didn't help. You can see it.
When the angle changes.
The angle changes. It put like, might be this guy, and it needed a confirmation from me. Then it said yes, right? So it's not perfect, but it's pretty helpful, I guess. So hopefully I'm connected there. Let's just find some picture here. Another banderas here. So I'm going Google test. Let's just go pictures, Google Photos, images, and hopefully
turn on safe search first.
Hopefully I can safe search here. And just excuse me. Oh, this one. I don't have this guy on this side. Let's try this one. Or maybe this one. Let's see the ones I have, because it kind of was playing around. Yeah. I want to pick something different. Sorry about this. Maybe this one, right? I don't have this one. So I'm just going to save the image here. That name. And let's call XX is fine. And then you go in Picasso, it's supposed to so it's supposed to sense my drag here and automatically pick up the photo and show that on the proper class. I may not be.
That's one of the top unrecognized, unnamed.
This guy?
No, on the left side it says update at the top.
Oh,
That, yeah. There you go.
oh yeah, so it didn't work, huh? I guess it didn't work. You know, bad example. Sometimes it works, sometimes it doesn't. But anyways, it's using some kind of machine learning. I don't know which one it's using. I guess. But the main point here was, if you Google, for example, like in the Google News, they do clusters, right, to classify the news. And so, and their problem is that if it takes too long, it's old news, right? And they're dealing with massive amount of data. So they're using machine learning algorithms for big data. And for that, you're probably not going to use Weka, so you're going to use much more powerful tools. One of them is Mahout. It can work with machine learning at scale. They work on top of Hadoop, so you can use Mahout on top of Hadoop.
Doesn't Google also have like an image search?
Yeah.
You could go out and take a photo of somebody and like upload it in there, and it will pull up all the matches based on that. I've heard I have a photographer friend who does that to determine what sites are infringing on his copyright.
Amazon does it too for shopping.
Okay.
A picture of something outside and I'll tell you what it is.
Where to buy it.
So the other one that's question.
Yeah, so Hadoop would certainly work on very large data sets, but not like
Real time, not fast.
Yeah, exactly.
Yeah, it's not real time, it's not fast. For that you want to use Spark. So it's another big data stuff that is supposed to be real time, and it's getting a lot of momentum in this thing here. It uses this mlib underneath. Weka has an interface to mlib, so you can actually use, they exchange algorithms between. I don't know how it works, I haven't tried. But if you were interested in that kind of a big data and fast stuff, you probably want to look into Spark. There's also one from Berkeley University. They open source their math lab stuff. All right, so now we're going to talk about my use case there at Precor. So Precor, as you know, they make fitness machines, right? We have this thing called network fitness. Their marketing name is Priva. That means you have a fitness machine that it runs Linux, a dedicated thing, and you can log in, swipe your RFID, or just type username and password, and then continue exercising where you left off. You can download exercise programs. When you save it, you can save your workout and continue where you left off, and it's going to track your goals and all that stuff. So they wanted to prove me to say, hey, we need to show to the clubs that they buy this stuff, that it's more expensive. It's improving their retention. How do you prove that? And it's like, it's a little interesting requirement. The other one was, hey, we're mining data, right? We had this whole data mining stuff. Just show me useful stuff. Why are you mining this data? Show me useful stuff. And it's like, what useful stuff? So with machine learning, you need to first ask the question. You need to know what the heck you want to get out from the data. Because, as you know, you're going to have to collect the data to answer a particular question. It's not that just you can look at the data and gain insights, right? Maybe you can if you're doing clusters and you gain some insights, but you better actually ask the right questions and then capture the data. You're going to have to do a lot of data normalization and adjusting to machine learning algorithms, for example. So it's not just show me cool stuff about the data, right? You definitely need to know do data cleansing. The data, I'm going to show you an example here. This is live data. I mean, sort of like that. This is real data from Precor. Basically, it's exercise data. It's all anonymous data. They don't know who you are, but it knows if you submitted a workout. If you have decided to have a goal, for example, if you set a goal, let's say I want to lose weight, there's one classic goal you can choose. One of the questions asked is, if people choose goals, are they coming more often because they have a goal? That kind of stuff, right? So you need to look at the data and figure out, having a goal is awesome because it makes you exercise more. Let me show you here with Weka the exercise data from oops, back to B process, open file. Let's go back here to not this one. Where is my data? Oh, Paulo Avelar. All right, so okay, so this one has 10,000 instances, right? And the data set is, this is the stuff that we're collecting. So you got gender, age, measurement system, and if you're like US or metric or other measurement systems, if the user has an RFID or not, if a user has a fitness goal, or the age of the account months when you created this account, location, name of the last workout, where did the guy work out last, country, latest focus. The focus is one of the things you're choosing there when you sign up for a workout. And then fitness equipment category, there's different kinds of fitness equipment. They have AMT, treadmill, and so elliptical, and so on. So in the number of workouts some people perform, the cardio workouts and strength workouts and whatnot. So we have like a game engine that awards people, points based on their meeting their goals, gives them badges, and it's just some gamification to maybe, help with incentivize people to exercise. So and then there's this thing, what I wanted to predict if people are using their accounts or not, right? But if you look at this data here, check out the age. It's all over the map. So if you edit this, and let me sort by age. Well, reverse sort by age.
What's the blue and the red distinction?
The blue is active versus not active.
Oh, okay.
It's the class thing. So, well, this is data that has been pruned. So I show you the wrong one, but it's been pruned. In reality, we have people with 2,000 years of age, 3,000 years of age, and like that. Because people just they don't want to enter their age, right? So they scroll the thing there, and 3,000 years. So then if you start mining the data, it's totally meaningless. So in the real world data is going to be 30. So you got to do a lot of data cleanup. And you may need to even change your application. Why ask people age? So there's the safe harbor thing. How are you going to know it's older than 13 years old or not, right? Why ask the age? So when you're trying to know too much information about the user's not going to give it to you. So that's, at least I don't when I go online. I try to be anonymous as possible, right? It's the same thing. So the only things that are really real, it's the data that the machine is sending. Like it's computing based on, I work out for an hour. That's real, there's a real clock in there. You can trust that. But user data, maybe, right? Maybe in the grand scheme of things, it doesn't really matter. So anyways, I had to do a lot of data pruning. And this data here wasn't in a single database. Because the way that these machines work, some things are in log files, some things where, when you design the system, you're designing persistence for the application in mind. You're not designing in terms of what data we collect to answer a given question, right? The design is very, especially if you're using a relational database. Maybe if you're using some key value pair data storage, it's easier to grab this stuff. But I guess what I'm trying to say is, in our real world, there data, the persistence was done for an application in mind, not for data mining. So you're going to have to create your own table, collect information from, run your own queries, and set up it so you can run the machine learning stuff. So that's what we did. So it's going to take some work. You can't just say, hey, give me cool answers about the data, right? You need to do data prepping. So that's what you have to sell to your boss. So it's gonna, And then, if you look at these other places, there's a lot of data missing here. It's just you don't know the location. Because the user can enter information from a mobile, there's a mobile app, they can just log in workouts. They forgot to, they didn't sign up at the gym, or they did some running that they did outside of the gym, and they just want to count that towards their goal. They can go in the mobile app and enter that. But we don't capture the location from the mobile app. So we could, but we don't do that. So it's going to be blank. So it's not going to help much. So there's a lot of data cleansing that has to happen. Anyways, if I run this to classify here, and I'm going to choose J48, and I start, it's still fast, and it builds some interesting tree. It ignores some other attributes. Let me show you. So basically that's the tree that it built. If people had awarded less than 713 points, they quit the gym. They're not using the account anymore. And what it's account being active, my definition was accounts that are more than 45 days. If you're not going back to the gym 45 days, I made that decision totally randomly. I was not the domain expert in the case. I was just building this as a test. So later on, we find out by asking the real club owners that that's not a good metric. A good metric would have been 6 months, because people do other activities, and they said, based on their own observations, you should have picked 6 months. So the other point is that if you don't have the domain knowledge, picking up data, it's going to give you predictions that are meaningless. So you better know the domain, know about the data, do a lot of data cleansing, and
Don't you need to exclude some of this data though too? Because I mean, if you're trying to figure out if somebody is active, and you're using the total number of workouts as one of your base selection criteria, of course if they're going to the gym all the time, they're active, then they're going to have a lot of those. And if you say, well, if they've got a lot of those and they're active,
yeah,
you can say, well, that's sort of.
It's true. So
it's not the tree of the circle.
Yeah, that's. I'm sorry?
It's not the tree, but the circle.
Yeah, definitely. So it's important to know about the data and pick up the proper attributes, be able to answer the questions you want.
So can you tell the tree analyzer to ignore certain things, or do you just have to take it out of the data?
No, you can take that out of the data, and you can apply filters. So I didn't show you here, but early on this whole process, there are many things you can do. There's a filter you can choose, and several filters you can. Let's say supervisor filters, an instance or attribute filter. So you can do, let's go to unsupervised.
If you have the data like for each month, how many points do they have, and when they quit, then you could predict if a point has lots of, if a guy has lots of points, is he more or less likely to quit the following month?
So bottom line, you can say remove one attribute. You can quickly go here and delete an attribute or add filters. You can change their values. You can normalize them. There's all kinds of transformations you can do. And the Weka tool can do this for you. So if you either going to make do data cleansing before you put in your data in your new data you're constructing as part of your data process, or you let a tool like this to do the work for you. You can programmatically pick filters, and those filters will eliminate things that are redundant and so forth.
Do you find it easier to use the data to prove or disprove a hypothesis rather than actually trying to explore to see what's there?
You have to actually prove. You have to observe in the field, like take the actual real responses, real.
I mean, you're probably looking at data for something, you're probably trying to find certain things, and you would tailor to try to prove or disprove what your assumption is.
Yeah, yeah. So, anyways, let's see what else I have here. Oh, the other thing that we're going to use this for, it's for warranty stuff, right? The people in the field, they have to replace belts. They want to kind of predict when the machine starts fading, when I have the belt replacement. That's a good use for this. So we're actually changing because the problem is collecting that data. So there are these sensors in the machine that when the operator goes in there and replaces the belt, he has to hit some button. That will send us a ping, say, hey, the belt was replaced. Because you can't rely on the technician to go in the database back and input the data in. He's not going to do that. So there is automation going on now on the newer generation of machines to basically be able to better know if you're losing money with warranty or not, and predicting when those things start to fail. So that's where we're going to be using this more. This user belongs to the gym or not. It was just an exercise to get into it. We can't really say because we're not at the gym. They don't have any user sign up to pay or not pay, right? So we can only tell if you create an account or not, just account information.
Why have you been doing that for years? Is it because of the cost?
Well,
simple sensors to be able to tell you how long ago.
It's cost. It's having a sensor. They have to design a machine, put the sensor in, then they have to program something to actually capture the sensor data and send over the internet, right? All that stuff is important.
So it just plugs it in and says, okay.
It plugs in, but then I don't have the data. It has to give the data in, right? So now that you have network machines, which is not until 4 years ago, you didn't have those machines networked. Now you can collect that data and do that.
So how long do these machines live on average?
I don't know. That's great stuff.
It's like you
As a
say,
developer,
on
I'm
average,
totally aware of that.
they kept it like 10 years, and it wouldn't be surprising that
I think it is pretty long.
I know they're pretty robust machines. They're mostly targeted to cloud operators. They're not your home fitness machine. So they take a bit in there. But there are NFL players, for example, people that they really stress. They're big guys, right? So they go in those machines and they do this running super fast, and then they slow, and then they run fast and slow, like there's a name for that game.
Intervals.
Yeah, and that basically kills the motor. So if you're a big guy like this, you don't have machines for 300, 400-pound guys, for example. So that's also interesting to know the way the person that is using the machine, why it is breaking. So one thing we're talking about a lot is, hey, we need to add a scale on these machines. They haven't done that yet. But once they start to see the benefit of collecting that information to help fix the machines on, it might be going a little bored to it. I don't want them collecting my weight, right? So that's a little bit of a.
And they start telling you when you need to work out more.
Yeah.
So they're gonna tell
You
you
don't
you're
want that
pregnant.
stuff.
You can't get off yet,
I don't know, I'm not doing the design on the machine. So, but it gets fishy if you're trying to do too much, right? So you want to be slightly down. Then you're gonna be the next target, right? Hey, you're too fat. Congratulations, or something like that.
They should collect, I mean, they already collect your weight. They always ask you how much you weigh and how long you want to run for. And they can detect your heartbeat, so they should have the technology.
Yeah,
to
but
scale it.
it's volunteer. If you decide to give
Yeah,
that
okay.
information or not, you're including it. So what we're talking about here is the machine collecting without asking you and measuring it. So that you would have real data, because you can't really trust user data, right?
Right.
the heart rate, maybe your neighbor's heart rate anyway.
Well, you happening, we were talking about the sensors for when things need service. That's actually one of the earliest applications of machine learning was in machinery using accelerometers. And you can't just look at the data and say, oh, is it good or bad? You have to use you need a filter, which in the old days people would rig things up, but you can now just record some data and train up a thing. Oh yeah, we've got so much time. And also, like if they replace the belt, you've got the accelerometer, and you can say, oh well, they replaced the belt even if they forgot to tell you. Right?
Yeah, exactly. The belt, we actually have a, what do you call the thing that counts RPM, like how many times?
Tachometer.
Yeah, we have that on the machine, so we can use that information. But there's a problem there with the resetting of that or not. Some people forget, if you replace the belt, if the belt technician forget to reset that, it's still using the old data. So the odometer is still counting as if, an old car that got some tire replaced, and it doesn't. Yeah, so the problem is in the field, data is going to be dirty. So to run those prediction algorithms, you really got to start trusting your data. And it's going to be statistical anyways. So the more data you have, chances are it's leaning towards something correct. Anyway.
Do you have any GPS chips in the machine in case one of the machines disappears?
No, sorry, no GPS. They're pretty heavy, so we can't disappear that easy.
Is there stuff for doing time series type analysis?
Yeah, there is. There is time series analysis. There's a whole lot of them. I only showed 4, but there's a whole bunch in here. And you should also look into other tools. There's one that's called K-Mind or something like that. It's also Java-based. It's an Eclipse. They built using the Eclipse framework. Over there, they emphasize a lot of the ETL thing, extract, transform load. So you can set up a data source just by adding, dropping, drag and drop icons. They call them nodes. Feed the data source feed this machine learning, or feed this other transformation even before you run the machine. There's a lot of ETL steps in this tool. And they also add a lot of really cool visualizations. You can run reports. There's several tools out there. In the Java space, this was interesting to me because it was readily available. It's good Java doc, and you can generate the code. It's super quick to test stuff. And you can quite quickly build a classifier, take the generated code and apply to real data. You can just observe how well it's doing. Anyways. So, I'm just going to jump to the conclusions here real quick. The data mining process, people think just take data, feed to Weka, and you got a cool result. That's not true. You basically need to know the question you're asking, collect the data, ask the question first, right? And collect the data to answer that question. That's the data science piece. Then you're going to do data cleanup because you're going to find out your real data is murky. And then you're going to define new features based on the data and perhaps create derived data. And then run Weka and then deploy. So Weka is the simplest piece of this whole thing. The complicated is collecting the data, find out. It's mining, it's in the mine, right? It's extracting information out of murky data. That's you're going to spend 99% of your time. So, yeah, that's basically summing up that. Oh, this is a cool, you guys know, what's it called, the Hacker News, right? There's this Hacker News style for data mining only. So you go in there, people just talking about all kinds of things in data mining. It's datatall.com. So, yeah, it's an interesting site just for, if you're doing data mining, data science, that kind of stuff. But I have some links here, will be there in the presentation. One thing that it's cool though, I didn't show you guys, this is final slide here. Hopefully it's in use somewhere. Yeah, I found this thing while I was learning stuff. It's this guy ranting about, I don't know if you can see from there. He was so it's the guy ranting about data scientists. And he's basically saying that, hey, it's all BS. You're not a data scientist. It's just companies trying to sell you stuff. So be aware of that too, because there's a lot of people, it's the same people that try to sell crystal reports. Hopefully there's no one here that makes crystal reports.
Yeah. You can say to your boss, hey, I found this great out. Look at this data, look what it's telling me. And then you say, well, if you want to prove it, you have to sit down for hours and actually explain to
Well,
them.
how do you prove when you have a lot of data? It's big data, right? How do you prove something in big data?
So you can just keep your job.
I don't know.
Eventually, the reality will disprove.
You were mentioning ETL. Weka is actually maintained by Tahoe now. And so they have, so they have some cool ETL tools like.
Oh yeah.
And so they've integrated Weka with the Tahoe kitchen.
That's great. One of the things they have here, I don't know if this is on the latest version or not, but let me show you here real quick. Since you mentioned it, they have in the tools. So here's a package manager. Come up. So there's a whole bunch of new algorithms you can choose and download and install the packages here, right on the framework. You can also, the knowledge flow is what you're talking about. you can build workflows. You can collect data. You add nodes here to collect data. You feed it a data source. It reads from your database directly. I did that at Precor actually. And then you apply more than one machine learning algorithm. You can create a pipeline basically, you know. And then based on the best result, you can choose one or the other. There's all kinds of stuff you can do this. It's quite interesting, I guess. But not a lot of programming involved, only on the final phase, when you want to actually deploy this into production. So that's all I have, guys.
So it looks like Precor is collecting all this amazing data. So if I'm using those machines, can I get hold of this data to do my own data mining on my data?
So
do you have some API or data export?
Just to answer, so we're building there's a public API. It's not really public because you have to tell who you are. So it's not like you can develop. So, but we are not doing data mining yet for real outside of it's not exposed into APIs. This was basically a showcase of the technology there. They're going to start doing it perhaps for this the warranty stuff. So we're not doing any data mining with users' data currently.
But do you get, is there a way for users to get hold of their data if they want to do anything with it?
No such thing.
Well, there are personal web services like with the activity trackers. That's actually a booming business right now, which is people to quantify life and that kind of stuff. So if you've got like the Nike thing with the shoe and your iPhone and all these different activity trackers doing exactly this. You go there. I'm forgetting some of the names, but just saw them last week.
So well, Nike is a bad example because they don't or hardly give anyone access
but
to
there's
their
these
API.
new trackers, right? And so you can work with a web-based data service with nice, pretty visualizations.
Jawbone, Fitbit.
We have partners with other, like we have an API that can access the user data, workouts submitted and whatnot, and you can choose to give your data to say Fitbit, for example, or it's one of the partners. If you allow them to access your data, then they can start tracking your workouts in addition to the things that Fitbit tracker itself is tracking. So they can combine that, give this holistic view of, how well I'm doing in terms of my fitness goal stuff. So that exists. But the API, it's done on a partnership basis. So you can sign up for and request an API access.
But you only get it if you play golf with your CEO.
I don't know. It's out there. It's in the public, but it's still through that process. So there's someone managing that partnership stuff. Right now, I know it's free, but I don't know if they have plans to actually monetize it. I'm sure they have, but they're not into that business yet. Core only sees them selling machines at this moment and collecting all this data for serving the user better, if you will, in terms of tracking progress, goals. But they're not monetizing that piece per se. Maybe it helps to sell machines to clubs because you have a fancy machine, but they're not, I guess, using that as a monetization strategy. There's people that are doing business out of APIs. That's not pretty cool. Anyways.
From your experience, how computationally intensive were some of these things? I mean, when you were...
I used here a 200,000 instance data at Precor. I had to have 8 gigabytes of RAM. I tried with 5, didn't work, so I upped my JVM limit to 8, and 8 was able to run because it needed all the data in memory. And it took way less than about 3 minutes on this Mac to do 200,000. A little less than that, 2 minutes or something. Actually, it's pretty quick. I can actually show you. So it's pretty fast. Let me show you a very complex tree, and then we end it there. It's getting late. Oops. Oh, not Weka. It's Paulo Avelar. So one of these files here is pretty large. Oh, too bad I can't see the size. But let me try this one. Yeah, 190. Yeah, 3,000. Right. I guess big data, 200,000 instances, but it loaded this whole file, and it has 15 attributes, and you can actually edit this stuff here, so it's pretty big. And if you run, the data here is messy. If you run a classifier here, with 10-fold, which is going to do it 11 times. 0R, I didn't mention, it's a baseline classifier. I should have shown this 0R. Baseline means if you were to take a guess, right, it's 50-50, it's just going to choose one. So it's used for comparison purposes. You want to actually verify your machine learning, compare it against 0R, if it's doing better or not. So it's a baseline classifier.
Is it better than flipping a coin?
It's the same as flipping a coin. It looks at it as there's 50 yeses and 10 no, it's going to choose 10 no. That's all it does, without even thinking. So that's the 0R, no roll. It chooses the one that has the most. And you use that to compare your classifier against this one. If you're not doing better than 0R, your data mine is all screwed. So don't even go data mine, just, you know. So that's a good thing to do. It's always compare against the base classifier, which is the 0R stuff. But that's not choose 0R because it doesn't do anything. If you do a J48 here, now you can see the bird is thinking a little bit. See that? It's spinning its gears. Because you have 200,000 instances there. And then but it's not too long. It's going to show up pretty fast. But it's going to do this humongous tree because this data wasn't pruned yet. There's a whole bunch of bad stuff in there. Oh, it's still not done, but it's building this humongous tree.
So what kind of tools do you use to prune the data? Is this just?
Oh, that's I was using Spring data to quickly write queries and collect things. You know, Spring data. I set up multiple data sources. We use relational data as well as columnar data and Amazon's. What's the name of that column data store there? Huh? No, it's the one at Amazon. DynamoDB. And DynamoDB. So we set up a few data sources, then we collect all the data and dump into a single table. So, and then we run some post-processing on that data, filtering stuff. Then we feed it to Weka. That's how I was doing it. But anyways, it's taking some time. It's maybe 3 minutes or 5. It will be done here. The point is, you won't crash. It still works. But typically, if you have a very large data set like this, you would chop your data and run Weka one data, run another. You know, so you can still do it. You just have to chop it instead of feeding this humongous data into it. So the visualize, you're not going to be able to visualize. If you visualize the tree, there's too many nodes. Anyways, but it generates the code. You can run this.
Cool. All right.
Yeah.
Unless there's any other questions, thank you, Paulo.